do you understand by gravity?
Most of us understand gravity but its effects.
For example, when we throw an object into the air, we see it falling down.
And when we drop anything from a height, we see it falling to the ground.
So the famous incident attributed to Newton of an apple falling on his head, though we understand it never really happened, right, Newton?
No, it never happened to me.
So we understand that gravity as the force that pulls everything down to the center of the earth.
So what really is gravity?
Well, in this series of videos, let the simple scientists,
AKA the Gravitational Masters,
unravel the mysteries of gravity. So, what do you understand by gravity?
Most of us understand gravity but its effects.
For example, when we throw an object into the air, we see it falling down.
And when we drop anything from a height, we see it falling to the ground.
So the famous incident attributed to Newton of an apple falling on his head, though we understand it never really happened, right, Newton?
No, it never happened to me.
So we understand that gravity as the force that pulls everything down to the center of the earth.
So what really is gravity?
Well, in this series of videos, let the simple scientists,
AKA the Gravitational Masters,
unravel the mysteries of gravity. Hi Newton, tell us what you know about gravity.
Well, I completely describe the action of the force of gravity between two objects' mass. I came up with the famous Newton's law of universal gravitation.
So, tell us about your law.
It's simple, really. You see, every object in the universe attracts every other object with force directed along the lines connecting the two centers of the objects. The size of this force is dependent on two factors. One is the mass of the two objects. The other is the distance separating the two objects.
Wait, can you explain more, Newton?
Sure can do. In simple terms, it is this. Firstly, the larger the mass of the two objects, the greater the force of gravity acting on the two objects. Secondly, the further the distance between the two objects, the weaker the force of gravity between the two objects. Simple enough?
Well, maybe you can give us an example.
Let's take you and me, Einstein. I'm about 40 kg, while you're about 150 kg.
150 kg? No, Mr. Newton. I'm only just 80 kg.
Sure. So now there is this force of gravity between us as a result of our two masses of 40 kg and 80 kg.
Okay.
So what if you are really 150 kg? Then the force of gravity between us will be stronger than the force of gravity that is currently pulling us together. So basically, the larger the mass of the two objects, the stronger the gravitational pull between the two objects.
Okay, that is clear enough. What is the second part of the law again?
Assuming now we are further apart. So instead of 20 cm away from each other now, you are 1 kilometer away from me. So let me ask you, is the force of gravity between us now when we are only 20 cm from each other stronger or weaker when we are 1 kilometer away from me?
Of course, now that we are nearer to each other, the force of gravity within us is stronger. If we are 1 kilometer away from each other, obviously it is weaker.
Now you understand my law, Einstein.
Excellent, Newton. Now, I understand you have described, your law actually describes the force of gravity that acts between two objects with mass. But it seemed to me like common sense. You mean to tell me that you came out with this and call it your law of gravity?
Well, I didn't say it was my law. I just stated the law. Other people say it was my law. So don't be jealous that you did not come up with it first. Ha 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 ha.
Sure. Now, so you described completely how the force of gravity acts on two objects with mass. But do you know what exactly is gravity?
Well, to tell you the truth, Einstein, I have totally no clue what gravity is. I only describe the force of gravity that acts between two objects. In my law, scientists can use it to send people to the moon and Mars. So I leave it to you to see whether you know what gravity is, Mr. Einstein.
Well, yes. I found out what gravity is and I will explain it to you in our next video. Welcome back, Newton. Now that we all understand your law of universal gravitation and how two objects interact with each other in the universe, let me share what exactly is gravity and how it works.
My heart is in suspense. Tell us, Einstein.
Awesome! Well, I have this theory about gravity.
Wait a minute. You mean it's not a law but a theory?
Hmm?
That means my law is superior to your theory. Because the law is like we all have to follow it, but the theory is just a guess, right?
Wrong, Mr. Newton. In science, a law is not higher than a theory. In fact, let me explain why mine is called a theory. Well, actually, let me introduce you through three scientific terms. They are hypothesis, theory, and law.
So why are these terms important, Einstein?
Well, let me explain. As scientists, we differentiate between these three terms. In science, a hypothesis is a limited explanation of a phenomenon based on some observations and research. It is a proposed explanation based on some limited data and can be further tested through more experiments and data that can either confirm it or reject it. A theory, on the other hand, is an in-depth explanation of an observed phenomenon backed by numerous confirmed observations, data, and experiments. So a theory is always backed by evidence, while a hypothesis is what I would say a work in progress and needs more data and more experiments to confirm it. A law is just a statement or description about an observed phenomenon, and typically we describe it by mathematical equations.
Wait a minute. How can you say my law is just a statement? Put in so much effort to come up with the law, my friend.
Well, Mr. Newton, don't get your bowels in an uproar. Let me explain.
Okay, please explain.
Now let's take an example. Precisely with gravity. You came out with the law of universal gravitation. This law describes exactly how two objects in the universe interact with each other through the force of gravity between them. This law also mathematically describes the force of gravity acting on the two objects. However, this law does not explain what gravity is and how it works.
Well, you don't tell me that I don't know what gravity is. Yes, I don't know what gravity is. So please explain why your theory explain what it is.
In fact, not only did my theory explain what gravity is, it also explains how it works.
Okay, stop boasting, Mr. Einstein.
No, really. My theory of general relativity will explain what the phenomenon of gravity is and how it works. That's what theory does.
Okay, let's get on to the theory and explain what gravity is.
Sure. I will explain my theory in the next video. So, let's summarize what we have learned about these three scientific terms. In summary, once we are sure how a phenomenon works, we can then describe it by a law. We can describe it verbally or more often with a mathematical equation. A law is something that always holds true when tested. However, at this point, we may not fully understand what this phenomenon is. So, we then worked out a hypothesis to explain what this phenomenon is, and we based it on some observations and experiments. However, it is still not comprehensive yet, and new data might confirm or reject it. But once more data and experiments confirmed the hypothesis, it can then be upgraded to a theory if it comprehensively explains the phenomenon. Now, let's take an example with gravity. Newton described how gravity works with his gravity equation. He said, gravity is a force which is dependent on the mass of the two objects and the distance between the two objects. However, Newton does not really understand what gravity is. Both Newton and other scientists tried to propose many hypotheses on what gravity is, but it took several hundred years before Einstein finally explained what gravity is and how it works. He came out with the theory of general relativity to explain what gravity is. So, there you go. Hope that you can now understand these three scientific terms and it will help you make sense of the concepts. Quiz time. So, can a theory be then rejected after it has become theory? Well, yes. It can be rejected if more evidence comes up to reject the existing explanations. Thank you for watching, and please look out for our next video on Einstein's theory of gravity. Please like, share and subscribe to our channel and click the bell so that you will not miss our upcoming videos. Thank you.
Okay, please explain the theory of general relativity and how it relates to gravity.
Well, I'll be glad to. Let me start earlier in 1905 when I published my theory of special relativity. In this theory, I showed that space and time are connected in a concept called the space-time continuum. You can model this space-time in two dimensions. That's what you see, this fabric here, right here. I call this theory as special relativity because it only applies for the special case when the objects are moving at constant speed and if space-time is flat and not curved.
So you are saying that space and time is like this fabric you are showing here?
Well, yes and no. You see, this fabric is an approximation in two-dimensional. Space and time is actually four-dimensional. You have the three dimensions of space, which is length, breadth, and height, and one dimension of time.
Okay, so is there other cases beyond this special case of constant speed and flat space-time?
Indeed, there are many. So it culminated in me coming up with the general theory of relativity in 1915. So this is where I finally managed to describe what gravity is.
Okay, tell us.
So in this theory of general relativity, massive objects can actually cause a distortion in the space-time fabric. Let me show you. If I were to place this object in this fabric, what do you see?
I can see a dent in this fabric.
Now, let's put in a bigger and more massive metal ball. What do you see?
The dent is deeper.
Now, let's put two of these metal objects. You can see that it caused a bigger dent. So, massive object caused a dent in space-time fabric. The more massive the object is, the bigger and deeper the dent is. This is what is explained as one of the consequences of my theory of general relativity.
Okay, so massive objects cause dents in space-time fabric? But what has this denting got to do with gravity?
Well, that is what we will explain in our next video.
Okay, before we go to the next video to understand how this bending of space-time relates to gravity, let's understand a little bit more about the bending itself. What we see as the bending of space-time using the metal balls is just an approximation in two dimensions. We can show it in four dimensions though, as it is not easy to simulate the time factor visually. So, the next best thing we can do is to show an approximation in three dimensions of space-time. This visualization will show you the bending in three dimensions. I hope that it helps you to visualize the bending. Thank you for watching, and please look out for the next video that explains how this bending relates to gravity. Please like, share and subscribe to our channel and click the bell so you will not miss our upcoming videos. Thank you.
Okay, so how does this then relate to gravity?
Okay, now Newton, please place the marble on the fabric. Now I'm going to place this medium-sized metal ball here. What do you observe?
I see two objects moving towards each other at a certain speed.
That's correct. Now what you see in terms of the objects moving towards each other is what we see as the effects of gravity. If there was no then, and the fabric of space and time was totally flat, then these two objects will not move towards each other. It is because massive objects bend space-time and cause it to curve that we see objects now moving towards each other. That is gravity. Now, let's repeat this again with a larger metal ball. Okay, so I will place this marble here. Okay, and you will place.
And I will place this larger metal ball here.
Okay, let's see that again. Alright, so I will place this marble here.
And I'll place this here.
So what do you observe now?
It seems that the two objects are moving faster towards each other.
Well, precisely. And this is what your law of universal gravitation explains. That is, the larger the two objects are, the stronger the gravitational force between them, and we see this as the speed at which the two massive objects are moving towards each other.
Now I understand why you said the theory explains what gravity is and how it works.
In fact, I can explain the second part of your law too. So let me replace this metal object with an even more massive object to demonstrate. Now, what do you see?
The dent is so much deeper.
Well, it's more than that. You see, as you get closer to the massive object, the slope of the dent gets steeper and steeper. The nearer the object is to the massive object, the steeper is the slope, and the faster the objects move towards each other. Now, this confirms your law that as objects get closer to each other, the gravitational force gets larger and larger.
Wow, that is amazing! How you can now visualize what causes gravity and how my law of universal gravitation now actually works.
Well, glad to be of help, Newton.
So, I hope that you can now relate the bending of space-time with the effect of gravity. Einstein's theory of general relativity says that massive objects bend space-time. This bending has a consequence to what we see as the effect of gravity. If massive objects did not bend space-time, objects do not move towards each other. But because massive objects bend space-time, objects then move towards each other, and we see this effect as gravity. The more massive the objects are, the larger the bending, and we see that the speed at which the objects moved towards each other increases. That means that the effect of gravity increases when the objects are more massive. Also, the slope of the bend is actually not constant. As we move closer and closer to the massive object, we can see that the slope increases with ever-increasing gradient. Hence, objects actually gain speed in our experiment as they near the massive objects because the slope is getting steeper and steeper. This is as described by Newton's law of universal gravitation, that the force of gravity increases as objects get closer to each other. So, we hope that you have found this visualization of the bending of space-time and how it relates to gravity useful in your understanding of the effect of gravity. Watch out for our next video on the movement of celestial objects around a more massive object such as the Sun and how we can visualize this easily in our experiment.
do something even more interesting.
Okay, let me place this large metal object in the middle.
Yes, if I just place this marble here, you will see that it will just drop into the middle of the massive object. Now, let's see what happens if I give it a little push. What do you notice now?
I see the marble going round the massive object in the middle.
Yes, this is how all celestial objects move around a more massive object. The Earth, for example, does not just drop into the Sun. It actually orbits the Sun, and you can see that it goes round and round because it has velocity. Now observe it more clearly. What do you see about the object? You see that as it gets closer to the massive object, it gets faster, as predicted by your law.
Yes, it does.
That's because the slopes get steeper and steeper as it gets closer to the massive object. Now, what's the other thing you observe? Let's see that again. What's the other thing that you observe?
Oh, I noticed that the orbit is getting smaller as it goes around the massive object.
Precisely.
This is different from how the Earth's orbit means approximately the same distance from the Sun.
Well, it has got to do with another one of your laws, Newton.
My law? Which law?
Well, it is Newton's first law of motion.
Oh, that one. My law states that an object at rest stays at rest and an object in motion stays in motion unless the opposing force is acting on it.
Right. So what is that force that is causing the marble's orbit to get smaller and smaller?
I am not sure.
Well, it's actually friction. In our model here, our fabric has some friction. So energy is being lost due to friction, and the marble's orbit gets smaller and smaller. For celestial objects, there is no opposing force in space that is causing the object's orbit to get smaller and smaller. So don't you think that is a very fortunate thing for us humans on this earth?
Why?
Well, we don't want to be fried chickens, right? If the earth spirals into the sun after some time.
I hope you have found that interesting. Now let's continue our journey by looking at the effect of this movement of celestial object on the massive object that they are orbiting in the next video. Please like, share and subscribe to the channel and click the bell so that you will not miss our upcoming videos.
Okay, Newton, let's continue our discovery of how celestial objects interact with each other through gravity in space.
Yes, I remember we had this marble orbiting the massive object in the middle. This massive object can be our Sun, and the marble is some small planet or asteroid in the solar system.
Yes, do you see anything happening to the metal ball as the marble orbits it?
No, it seems totally oblivious to the marble's movement.
Great. Now, take this small metal ball and give it a push, Newton.
Okay, let me do that.
So now, what did you observe happening to the metal ball in the middle?
The large metal ball seems to be moving too.
Yes, it does. Now let's see that again. Okay, now let's try to use another metal ball of the same size as the one in the middle. Now let's see what happens.
Wow! Both metal balls orbit each other?
Indeed! That is awesome! Now let's try that again.
Yes! It looks so cool!
So Newton, the question is, when we were using the marble to orbit the large metal ball, did the large metal ball move?
No, I did not see it move at all.
Well, that's not entirely accurate. It actually moved, but because the relative mass of the two objects are very different, we can't actually see that the large metal ball actually moved too, because it was too tiny to be observable.
Is it?
Well, yes, it does. You see, but as this is similar to the tiniest objects in the solar system moving around the sun. As their mass is tiny relative to the sun does not seem to be affected by it. But once the two masses start to be close to each other, we can see that the two objects are actually orbiting each other. So we can see that the giant planets of Jupiter, Saturn, Uranus and Neptune actually cause what we call perturbations in the orbit of the sun.
Okay, why is that useful?
Well, we can use this to detect stars that have massive planets orbiting them. As the giant planets orbit around their stars, the star wobbles, and we can infer that the star has a planet orbiting them.
Planets orbiting a star cause the star to wobble. This wobble is actually due to the star orbiting in a small circle or ellipse. We can detect this movement by using highly sensitive spectrographs connected to Earth-based telescope. When the star moves towards the observer, the light detected shifted more towards the blue spectrum. When the star moves away from the observer, the light detected shifted more towards the red spectrum. In this way, we can detect massive exoplanets orbiting distant stars provided we are not looking particularly at the star, since we cannot see the star moving towards us or away from us.
You know, this is getting very interesting, but I want to show you a very neat phenomenon, gravity.
Well, shoot, Mr. Newton.
Okay, let's reverse things around. So instead of having the metal balls in the middle, I'll put this marble in the middle.
Okay, show us what you mean.
Okay, now I'll push this medium metal ball towards the stationary marble. What do you see?
Well, let's try that again. Let me see. Well, I see that the marble is actually being caught by the metal ball and starts to orbit it.
Indeed. Now let's repeat it with a large metal ball.
Wow, this is interesting. You see that the marble got caught and orbited even higher speed than previously.
Yes, that is how objects in space can be caught into orbiting the sun as they pass by the sun. Meteors are such great examples of such phenomena.
Well, that's so awesome.
Now, let's try another experiment. Let me ask you, Einstein.
Okay.
If I have this large ball and this small ball, which object will orbit which?
Of course, the smaller ball will orbit the bigger ball. Just like I am bigger and stronger than you, you will orbit around me.
Okay, let's find out.
Oops, what's happening here?
Well, no. If you have understood my law of universal gravitation, then you have known that gravity depends on mass and not size.
Yes.
So in the world of gravity, mass is king and not size.
Well, yes, this reminds me of the reason why a giant red star, 100,000 times the size of the sun, can be pulled into orbiting a smaller but more massive neutron star the size of just New York City.
Yes, so it is all about mass and not size when we talk about gravity. Now Einstein, things can get even more interesting with gravity.
Okay, what do you have in mind?
Now, let's assume I have this marble and it represents the moon. And I have this medium-sized metal ball which represents the earth. And this large metal ball representing the sun. We can do some neat things with this.
Wow, sure, show me.
So, let's push the earth and the moon together around the sun. What can you see?
Well, I can see that the moon is orbiting the earth and the earth is orbiting the sun. Let's see that again. Yes.
That's correct. But the question is, how can we explain this phenomenon?
Okay, this one I know. Basically, what happens is this. The earth is causing a small dent in the fabric of space and time, resulting in the moon being pulled around and orbiting the earth in the so-called well or dent. But because the sun, massive mass, is also causing a dent in the fabric of space and time, there is this larger well that is also pulling both the earth together with the moon to go around the sun.
Yes, in fact, there is an even bigger dent or well in the center of the Milky Way galaxy due to the existence of a supermassive black hole. It is called Sagittarius A,
Wow.
with a mass of 4 million suns
1 million?
or 4 million solar masses that is causing the sun and billions of other stars to orbit around this supermassive black hole.
So the moon orbits the earth, which then orbits the sun, and the sun orbits around the supermassive black hole in the middle of the galaxy. And all of these are caused by the bending of space and time at each location due to the mass of the objects.
Precisely. How amazing is that, isn't it?
Sure is.
Okay, let's show another experiment. If I were to push two marbles together at the same time around the large metal ball, what do you see?
Okay. Well, I can see that at first they are orbiting together, but now they are splitting apart as they go around the large metal ball. But after a while, you see them splitting apart, right? So what do you think caused this split, Mr. Newton?
Well, here is what happens. At first, the two marbles are stuck together as they orbit the central metal object because the gravitational pull between them is strong enough to keep them together. However, as they pick up speed to a steeper slope near the metal object, the increased velocity is enough to break the gravitational force that they are exerting on each other. Hence, they split apart.
Okay, you can see them splitting apart. There you go. See? Alright, so that is really interesting to see, Mr. Newton.
In summary, the effect of gravity on the orbit of celestial objects are as follows. Celestial objects orbit one another due to the effect of gravity. Gravity creates a dent or well around a massive object, and other objects with velocity get pulled to move around the massive object in this well. Hence, the Earth creates a well around it, making the smaller, less massive moon to orbit the Earth around this well. Similarly, the more massive Sun creates an even bigger dent or well around it, and the Earth, the Moon, and the other planets orbit the Sun around this bigger well. Finally, the supermassive black hole Sagittarius A in the center of the Milky Way galaxy creates an even more humongous well, resulting in all the stars in the galaxy to revolve around it in this massive well or dent of the space-time fabric. Next is why celestial objects got separated. In our example, the moon got separated from the Earth as the two objects came closer to the sun. This is because as the objects get closer to the sun, the well or dent get deeper, resulting in higher velocity of the two objects of the Earth and the Moon. The increased velocity at that stage is large enough to overcome the weaker gravitational force between the Earth and the Moon. This results in both objects breaking apart from each other and taking on a different orbit.
Okay, Newton, maybe we need to get back to the proof of my theory of general relativity as it relates to gravity.
Yes, I wanted to ask you, how do you prove that massive object actually cause space-time to curve or bend? Basically, I can't see that bending. So how can I be sure that your theory about this bending is correct?
Well, that is wonderful, Newton. In science, we always ask for proof. And since I put forward this theory, I also put forth some tests that can prove my theory about this bending of space.
Okay, so tell us what is the proof?
Sure. Now, I can prove this bending of space-time by the phenomenon of gravitational lensing.
What does that mean, Einstein?
Okay, let's do some experiment to show gravitational lensing in action. So, Newton, please push this marble towards me. So you can see that this marble goes directly to me, right?
Yeah.
Okay, now let's put this massive, large metal ball in the middle of this fabric. Now again, you notice the bending of space-time fabric. Now, please push the metal ball, the marble towards me. Oh, what can you see? Try that again. Did you see that? What did you do? Let's see.
I see the marble is curved away as it approaches the large ball.
Great. So, similarly, Einstein, predicted that light will be bent as it passes by a massive object. This is what I call gravitational lensing.
How does that prove that massive object bends space-time?
Well, it goes back to your law of universal gravitation. You see, based on your law, gravity works only on objects with mass, right?
Yes.
Aha! But you see, light is not matter, but it is actually energy, and energy does not have mass. So, in classical Newtonian physics, light should not be affected by gravity, right?
Yes. So how do you explain the bending of light as it passes through massive object?
Well, light only follows space-time. So if space-time is curved, because massive objects bend space-time, then it will just pass through the curved space-time. It is like when you're traveling on a road. At first, the road is straight. If the road curves, now would you follow the road and curve with it, or would you just go straight?
Obviously, I will go straight.
Precisely. So that is what light does. It just follows the road on the space-time fabric. It is not pulled by gravity, but instead, because of the massive mass of the celestial object, the mass curves space-time, and this curving causes the light to bend because it followed that curved space-time.
Okay, I am convinced now that massive objects curve space-time and that then cause the phenomenon we call gravity.
Precisely. So that, well, yes, and the amazing thing is that because of gravitational lensing, we are able to see objects behind massive objects like galaxies.
That is amazing! You mean I can see something like behind a wall?
Well, close. Basically, as you see in our experiment, the observer thought that he was looking at an object here, because we know that light travels in straight line. But, however, the object is actually behind the massive object here. So you are able to see it because the bending of light due to the curvature of space-time near to the massive object.
Thanks, Einstein. Now, I can go and make a gravitational lensing telescope to see behind the wall.
Newton, that's not what I meant.
Stay tuned to our next video on gravitational waves.
Well, Newton, did you manage to make your gravitational telescope to see behind a wall?
It did not work.
Okay, don't worry. Now let's further unravel the mysteries of gravity with a concept of gravitational waves.
You mean I can sum up my surfboard on these gravitational waves?
Don't be silly, Newton. Well, anyway, what is gravitational waves?
No idea. Tell me.
You see, we have shown that massive objects bend space-time, right?
Yep.
Okay. So now imagine that you are this massive object and you quickly and accelerate through space-time. Since we know that a stationary massive objects cause bending and distortion in the space-time, what will happen when this massive object accelerates through space-time?
I don't know. It causes creases in the space-time fabric.
Newton, you are actually right.
I am?
Well, in a way, you see, just like if I have this ball and I push it with increasing speed across this fabric, you can see that it causes creases on this fabric. Now I can show it better if I just drop this metal object on this, and you can see ripples moving out from this metal ball. Can you see that? Let's try that again. So these creases or ripples are what we call gravitational waves, and it actually moves away from the source and travels to space at the speed of light.
Okay, so what is so special about these gravitational waves?
Indeed, you might be interested in this. You see, as the gravitational waves pass through matter, it actually contracts and expands the matter. So, if a gravitational wave is passing through you right now, Mr. Newton, you will be actually taller one moment and then shorter in another moment.
Well, I just want to be taller and not taller than shorter.
Well, at least you can be momentarily taller than
Are
me.
you sure there are really gravitational waves? What is the proof?
Well, scientists are actually detecting these gravitational waves, for example, at the LIGO observatories in the United States. So far, they are able to prove the existence of several gravitational events. Such as those caused by colliding black holes. Now keep your fingers crossed for more gravitational events to come.
Keep your eyes peeled to the channel for our next video on black holes.
So yes, even though you can't ride on your surfboard on these gravitational waves, these celestial waves are indeed extraordinary. The acceleration of massive objects through space causes creases or ripples in the space-time fabric. Now these creases or waves travels outward from the source, which are these massive objects, at the speed of light. What is more amazing is the effect of these gravitational waves on matter. As the waves passes through matter, it actually causes matter to increase in size and decrease in size, corresponding to the movement of these waves. But these changes are so tiny that you need an extremely sensitive senses to detect. So far, we are only able to detect supermassive objects causing these events, such as the collision of massive black holes. Gravitational waves observatories, like the largest one at LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory, are able to detect these tiny changes. Detection requires extremely precise engineering with a precision of 10 to the power of minus 19 meters, or 1/10,000th of the width of a proton. It comprises two enormous laser interferometers, LIGO Hanford and LIGO Livingston, located 3,000 kilometers apart, and two research centers at Caltech and MIT. Now, these two interferometers are so far apart to cancel out the Earth-based vibrations so that the actual gravitational waves can be detected and separated from these local vibration noises. Now, how do interferometers work? It uses the physical properties of light and of space itself. Now let's go into more details. The first concept is the constructive and destructive interference of waves. Now, when wave collides, they combine or cancel out each other depending on how the two waves meet. If they are in sync, the two waves add up and the waves gets bigger. This is called constructive interference. Now, when the waves are out of sync exactly, they cancels out each other and the waves disappears. This is called destructive interference. Now, in real life, the waves will add and cancels at various levels depending on how in sync or out of sync they are. So there will be partial constructive or destructive interferences. The second concept is that gravitational waves affect space. Now, when gravitational waves goes through space, it will stretch space in one direction and compress space in the perpendicular direction. Hence, each interferometer's arm is designed to be perpendicular to each other to maximize the difference in lengths of the tubes that the laser will travel. So this is how the interferometers work. A laser light is sent to a mirror that will split the light into two light beams. Each beam goes into separate perpendicular vacuum steel tubes or arms which are 4 km long each. At the end of each arm, the light is reflected back and these two beams will be detected back at the beginning of the arms by a photodetector. If there is no gravitational waves, the two arms are at the same length. Then the two beams received would have traveled the same distance. They will then arrive at the photodetector perfectly aligned. Hence, the lasers cancel each other in destructive interference, and no light is then detected. If there is gravitational waves, the two arms are of different lengths. Then the two beams received would have traveled different distances. They will then arrive at the photodetector out of alignment. The lasers then arrive in various alignments and can have total destructive interference, total constructive interference, or partial interference as the two lights goes in and out of alignment. Hence, there will be flickering of the light as it goes through the gravitational wave cycle, and we see anything from no light, brighter light, and anything in between. This is how gravitational waves are being detected.
This is my favorite topic related to gravity, black holes.
Well, Newton, please do the honors of explaining to us about black holes.
Most certainly. Okay, since we know that massive object bends space-time, what if we have a really massive object? I mean, really stupendously massive object.
You mean like this object?
Yes. So if I were to place this on the fabric, what do you see?
Wow! I see that the slope of this bending is almost infinite.
Indeed, if you imagine that this marble is a ray of light, and you let it orbit this massive object, you will see that this marble has no way of escaping. Just like we said previously, gravity does not pull light into the massive object. Instead, the massive object bends space-time so much that light just follows the space-time.
Yes, so when the object becomes extremely massive, the slope of this bend becomes almost infinite, hence light is not able to escape this almost infinite slope.
Okay, besides light being unable to escape a black hole, there are some other interesting things happening near a black hole.
Tell us what they are, Newton.
Okay, there is an area near a black hole called the event horizon.
Okay.
We can assume that this ring is the event horizon
This one? Okay.
of the black hole. As light nears this event horizon, it slows down. At the event horizon, light actually stops. And time too. So if you want to be young at 25 forever, take a trip to the event horizon of a black hole. Wow. But make sure to stay exactly at the event horizon.
So why must I stay exactly at the event horizon?
Well, as you approach the event horizon, time slows down in a concept called time dilation, and light slows down too. At the event horizon, both light and time stops. Now what happens beyond the event horizon is scary.
What happens beyond the event horizon?
Well, it is still a hypothesis since nobody has been there, of course, and back to tell what happened. But some scientists believe that beyond the event horizon, light accelerates beyond the speed of light, and matter gets ripped apart and pulled into the singularity at the center of the black hole.
That really sounds scary, man.
Indeed. But let's have more fun with this black hole of ours.
Okay? Yes, let's throw some marbles into an orbit in this black hole. You can see, as you throw the marble, that it travels together and then it's split apart like a spaghetti. Yes, this spaghetti-fied. Come, let's try this again. You see this? Whoa! It's just cool, isn't it? And you can also see how the speed goes more and more as it goes nearer to the singularity in the middle of the black hole.
Well, watch out for our next video on why most objects in the universe revolve in the same direction.
Yes, you can see that all the marbles are gaining speed as it goes around the singularity of the black hole. Now, well Newton, let's do an experiment to answer the question why all planets in our solar system orbit the sun in one direction, in which case in our solar system is in the anti-clockwise direction.
They do? Tell me why.
Well, let's do an experiment. So I want you to take that cup of marbles containing 15 marbles, and I will take this cup of marbles containing another 15 marbles. What I want you to do next is to push the marbles in the anti-clockwise direction while I push the marbles in the clockwise direction. Are you ready? 3, 2, 1, go!
Wow! It seems like the remaining marbles are revolving in the same direction.
Indeed, it is probability, Newton. We will have some marbles colliding with one another, and after some time, we see the remaining marbles traveling in one direction, so either clockwise or anti-clockwise. In our case, it was clockwise, but in the case of our solar system, it is anti-clockwise. Let's try that again. You do in anti-clockwise and I do in clockwise. 3, 2, 1, go! Now you see it's traveling in the anti-clockwise direction.
That's cool and so much fun, man!
Okay, Newton, let's see which of these two objects will fall to the ground faster. Do you think it will be the bigger bunch of 30 marbles or the smaller bunch of 10 marbles that will fall down to the ground first?
I think it will be the bigger bunch of 30 marbles because they are heavier.
Well, let's find out. 3, 2, 1. Well, let's try that again and see what happens.
They both drop to the ground at the same time?
Indeed. Now, why do you think this is so, Newton?
I don't know.
Well, it is because they are both accelerating at the same rate.
Oh, I remember now. Assuming I have a truck and a car and starting a race. If both the car and the truck accelerate from 0 to 100 kilometers per hour at the same rate, they will be at the same speed at any point of time.
That's correct, Newton.
So, if they are both at the same speed to each other at the same time, and they both started at the same time from rest, then they definitely will reach their destination at the same time. In the case of the two marbles, they both drop from height at 0 meters per second and both accelerate at a rate of 9.8 meters per second squared. So at any point of time, they will be at the same speed. That is, after 1 second, they both will be at 9.8 meters per second. After 2 seconds, they both are at 19.6 meters per second, and so on.
Exactly. So hence they will reach the ground at the same time. But the question is, will be the force of gravity acting on both objects be the same?
Well, no actually, because one bunch of marbles is more massive than the other one. It takes more effort and energy to accelerate it at the same rate. Let's take the example of the truck and car again. So, even though both start at 0 and accelerate at the same rate, it takes more energy to push the truck than it takes to push the car.
That is correct, Newton. Awesome!